So there are other things that you can do to a system, but a lot of these things will actually not affect the equilibrium position. So one thing you can do is actually increase pressure by adding an inert gas. And we would say inert gas, that's something that does not, so inert gases do not react with other gases in the system. So it won't react with the X gas or the Y gas or the Z gas. So when you put those in, what it does is it actually does increase the pressure because there's more collisions between particles of the inert gas and the other gases there, and also more particles with collisions with the side of the container. But the thing is, it doesn't necessarily lead to more collisions between the reactant particles. It really just affects the reactants and products equally. So there's no need for one to compensate for the other. So as a result of that, because it affects both the reactants and products equally, and it really doesn't increase the collisions between the reactant and the reactant particles themselves, just more so between all the particles and the inert gas, it's not going to have an effect on the equilibrium. So there's no effect on equilibrium. No shift. No left to right or right to left. So in other words, our K is going to be constant as well. I mean, other factors affected the equilibrium, and there was a shift and K remained constant with the exception of temperature, but essentially this will not change K, this will not shift the equilibrium from left to right or the other, it's just going to stay as is. No effect on the equilibrium whatsoever. Examples of inert gas that we sometimes do use this for would be things like argon, neon, so essentially your noble gases. There's more, but that's just some examples. Also, nitrogen is a inert gas, especially when it comes to gases in these equilibrium mixtures. So that's one factor that does not affect the equilibrium in terms of shifting it. Another factor that surprisingly doesn't affect equilibrium is adding a catalyst. And I say surprisingly because we think catalysts can do everything. So catalysts, when you add a catalyst into a system, first of all, the K won't change. The K is constant. And what I want you to remember is that a catalyst reduces the activation energy for the system. And so what it does in this case is it's actually going to speed up both the forward and reverse reaction rates equally. So because it speeds both of them up equally, the other one doesn't have to compensate and it won't lead to a shift. So basically there is no effect on equilibrium. In other words, there's no shift because it affects both sides equally, the forward and the reverse. However, the one thing that it does do is that that you reach equilibrium faster. At the same concentrations, but faster. So for example, let's say I was up here. Here I reached, let's say, equilibrium at 3 seconds. If I had a catalyst, I'd probably reach equilibrium maybe, let's say, at 2 seconds here instead. They'd be at the same concentration. It would be a faster sort of rise and faster decline to those concentrations, but it would be earlier than the 3 second mark over here. So a catalyst will not affect the equilibrium in terms of making it shift because it speeds up the reactions forward and reverse equally. So there's no need for a shift to occur there. The only thing it will do is that it will allow the equilibrium to establish itself faster, but at the same concentrations that you would expect for the reaction with no catalyst. And so those are the factors that affected equilibrium and that led to shifts according to Le Chatelier's principle. We saw adding an entity or a species to the system So therefore increasing the concentration, or removing, which would be decreasing the concentration. And essentially the system wants to shift to counteract that. So if you add something, the system shifts to use that thing that you added up. If you remove something, the system shifts to produce more of the stuff that you removed. Increasing the temperature is another thing we saw, and we saw that the effect depended on whether you have an endothermic or exothermic reaction. So if you increase the temperature for an exothermic reaction, you shift in a way to reduce the heat that was added there. So you go to the left side where there's no heat. And if you decrease the temperature, you shift in a way to increase the heat that's there. So you shift to the right side for exothermic. Whereas for endothermic, we saw was the opposite, because the heat term is on the opposite side. In terms of the graphs, we saw that when you add a substance or remove for whatever that substance is, you'll see a sharp increase for adding, or sharp decrease for removing at the very beginning. And then afterwards, you see your drops and your increases gradually. Whereas for temperature, we don't see anything sharp because we're not adding anything. We just see our gradual increases for whatever side is producing, and gradual decreases for whatever side is losing. Then we also saw we can affect the equilibrium position by, or shift the equilibrium by increasing or decreasing pressure through the volume. So essentially, if we increased volume, we decrease pressure, and we want to go towards the side that has more particles to increase the pressure of the system. If we increase the pressure of the system, on the other hand, by, let's say, reducing the volume, we want to decrease pressure overall. So we have to go towards the side that has more particles, fewer particles, in order to reduce the overall pressure in the system. And what we notice about the graph is that when you do a change in pressure for the entire system, you're going to see a sharp increase in their concentrations over time at the beginning, because you increase the pressure for the entire system by reducing the volume. And so it leads to a sharp increase of the gases at first, and then afterward you see your decrease and your increase gradually. Then we saw some factors that you could change but would not affect the overall equilibrium in terms of shifting. So we saw adding an inert gas like noble gases or nitrogen. They don't react with the gases in your system. They do affect pressure. They increase the pressure overall because now you have more collisions between your reactant particles and whatever particles are there with the noble gases or the other inert gases. But it doesn't really increase the collisions between the reactants and the products as needed. So really it affects both the reactants and products equally, so there won't be a shift. And then lastly, we saw catalysts. Catalysts, again, for there, the K stays constant. A catalyst actually does not have an effect on the position of equilibrium. It doesn't lead to a shift, and that's because both the forward and reverse are affected equally, so there's no shift there. But you do reach equilibrium faster. We saw that essentially all of these do not affect the K value, because even if there is a shift, that when the equilibrium is reestablished, if you do the K expression with the values that are reestablished, you'll get the same K value, with the exception of the temperature. The temperature actually does affect K value, because when you increase or decrease temperature, it affects your forward and reverse differently, since your forward and reverse are different types of reactions. One of them is exothermic, and the other side, if you went the other way, it's endothermic technically. So temperature is the only one that really has an effect on K overall. I did encourage you to go try to find and see what that effect is. So if you increase temperature, what's the effect going to be on K? If you decrease temperature, what is the effect going to be on K? Think about how that would apply to different reactions, either endo or exo, for example. And so you should be able to predict what direction reactions will go in based on different stresses that are provided, and also do rough sketches of graphs like this to illustrate how the system will correct itself to get back to equilibrium.